optimizing problem number 3. Start by identifying what I'm supposed to maximize. And I see right away, not that I want to move it, but I see right away, largest area of a rectangle. So maximizing area. Which is a base times a height. I gotta continue with this though because I see some other really weird things up there. A rectangle is inscribed in a semicircle of radius 2. Okay, so when you talk about a circle of radius 2, we typically think of it on an XY axis. And we only want the top of the circle because they are talking about a semicircle. And then inside of that semicircle, we have a inscribed rectangle. So some rectangle that's sitting under the semicircle. And it has a point on the semicircle. So we have some really big decisions here for variables. On this XY axis, I can see that no matter where that semicircle is, whether it's a skinny tall rectangle in the semicircle or a flat long rectangle, the point is going to be on the circle. So that's definitely going to give me some substituting values. And I can call the height of the rectangle the y value of that ordered pair that is sitting on our semicircle's outer edge. I also note that that ordered pair is x units to the right and equivalently x units to the left, or a distance of x units. So the base in this case is actually going to be 2x, or twice the distance from the origin. One in the positive, one in the negative direction. So the area is coming together. Let me just see if I can start to write the area function. Base times height. I'm going to call the base right away 2x because I love functions in terms of x. And I just need to think about how I can turn the height value, which right now is y, into an x value. And the key in this, I'm just going to make it super fast, and I will tell you that the function for the semicircle, because I know the function for a circle, is going to be the top half of the radius squared minus x squared. That comes from our original circle formula, which is x squared plus y squared equals radius squared. And I'm just manipulating it to only give me the y value. So that semicircle gave me a lot of details about how to write the base times height in terms of just one variable. And I really feel like this looks like problem number 2 when I go to take a derivative. I know it's going to be messy. It's a product rule. So I have the derivative is 2x times the derivative of the square root, which is 1 over 2 square root 4 minus x squared. Chain rule, the derivative of that interior radicand, negative 2x, plus the product rule, derivative of 2x times the square root function. Whew, another nasty derivative, but we've done it before. If we set a prime equal to 0, again, I'm just going to go back through this and clean it up a little bit again. And in this case, we don't have a half in coefficient. We have a 2 as a coefficient. So we have negative 2x squared over square root of 4 minus x squared plus 2 times the square root of 4 minus x squared. I'm going to manipulate this really quickly into another proportion, similar to solving the prior problem. That's chunky looking. And if we think of this as a proportion, we're looking at that right-hand side, a fraction over 1. So solving the proportion, that is really weird. Solving the proportion, we get 2x squared equals 2 times 4 minus x squared by cross multiplication. Some more solving. This time I'm going to move the x squared term all to the left. So I'm adding x squared to both sides. And we've got 2x squared equals 4. So x squared equals 2, and finally x equals the square root of 2. That's our critical value. And we're going to use that and plot it on a number line for the first derivative test. I'm still using the first derivative test because up here, this is not something I want to take a second derivative of. We could go back to the other method, which is testing the value of the critical value in the original function with its endpoints and determine maximums and minimums. I think this time I'm going to do that. So I'm going to use the critical value of root 2 and endpoints. And so I want to think about a endpoint decision, that domain decision for different x values. Critical value was the square root of 2. And this is the extremes or the extreme values method of testing for maxes and mins. Endpoint here, if we took that rectangle that's inscribed in this picture and we shrunk it down to a really narrow, really tall rectangle, we would get x approaching the origin and all the way down to 0. Now that would be a rectangle that is like a line, which clearly has no area. But we're getting an endpoint that we can imagine as a non-inclusive endpoint here. At the other end, if we expand x all the way out, and it still has to be contained under that inscribed semicircle, we'd be extending the rectangle all the way out to be a very flat, long one, but it's contained at the edges of the semicircle, and so 2 is going to bound our maximum value of x. When I go and plug this in, this time instead of testing left and right first derivative, I'm testing values in the original function. And so we're looking at this equation, plugging a root 2 in, 2 root 2 times the derivative of 4, or sorry, the square root of 4 minus root 2 squared, which is just 4 minus 2. That equals 2 times root 2 times root 2. Huh, that's 4. Okay, so that's the area with an x value of root 2. If we plug in a 0 into that area function, I see right away from that very first part of the problem, the 2x, I'm just going to have a factor of 0. And if we plug a 2 in, I see from the second factor, the root, the square root of 4 minus x squared, plugging in a 2 there is going to give me a factor of 0. So on either endpoint, clearly, if we have a flat triangle, or sorry, a flat rectangle, we have no area, area 0. This is going to indicate to me really quickly that I have the maximum value of 4 at the critical value of root 2. A little bit different than the sign chart that we get on the first derivative test. So let's answer the question, put it into context now. And a rectangle is inscribed. Find the rectangle's dimensions. So I have the x value of root 2, but the dimensions of the triangle are the base and the height. This is the dimensions. And the base value is actually, we called it 2x. So back at the area function, this was our base of 2x. So the base is really going to be 2 root 2. And then the height of the triangle was that square root of 4 minus x squared. Plugging in a root 2 there, we've got the square root of 4 minus root 2, which is root 2. So we have a base and a height. If you think about that on the picture, we've made ourselves a square on either side of the origin is the maximum value of the rectangle that's inscribed under a semicircle. All right, but let's finish that with some words. The dimensions of the base and the height provided will maximize, or will give the largest area. All right, putting it back into context of what the question is asking. At this point in time, if you've watched this video, I want you to email or text me if you think this is a good idea.